Hello and welcome to part 5 of PhaestusFox Does Adventive Code. In this episode I'll be doing day 7 and 8. So starting with day 7, you can hear birds chirping, raindrops hitting leaves as the expedition proceeds. Occasionally you even hear much louder sounds in the distance. How big the animals get out here. Anyway, the device the elves gave you has problems more than just the communication system. You try to run a system update and you get an error. Perhaps you can delete some files from the device for the update. You browse the file system and you browse around the file system across the situation to assess this situation and save the results to the terminal terminal output, your puzzle input. For example, you'll get a list of instructions. The file system consists of a tree of files in plain text or directories that contain other directories or files. The outermost directory is called /. You can navigate anywhere around the file system, moving into and out of directories and listing the contents of those directories. Anything with a $sign is a command that you enter. You can either enter the command to change directories, being cd x to move in to that directory, cd ... to move out one level, and cd / to go right back to the root. ls means list and will print out all the files and directories currently inside the directory you're in, and it will print a file with the file size and then the file's name, and then if it's a directory it'll write dir and then the directory name. Given that the input given above, you will get this as your file system. And it says that there are 4 directories. The outermost directory, A and D, which are inside that, E, which is inside of A. There are your 4 directories. Since the disk is full, you might your first step should be to find directories that are good candidates for deletion. To do this, you'll need to determine the total size of each directory. The total size of directories is the sum of the size of the files it contains, directly or indirectly. So if you have a directory inside a directory, its size gets added to the outside directory. So in this example above, the file I gets added to E size, so E would have a size of 584, and then A gets E size added to it along with F, G, and H. Okay, so that's that calculation here. To begin, we need to find all directories with a total file size of at most 100,000. Then calculate the sum of the total of these sizes. In this example above, the directory A and E, the sum of total is 95,437, which is the size of A plus size of E. And it says, even as in this example, you can count files more than once, since or directories more than once. E is inside A, but we counted A including E, and then we also added E again. So we technically counted the I file twice. So then I got a file count of 1,334,506. And then now you're ready to choose your directory to delete. The total size of the file system is 70 megabytes, and to run the update, you'll need space of at least 30 megabytes. You need to find a directory you can delete that will free up enough space to run the update. In the example above, the total size of the outermost directory, that's the total amount of space, is 48 megabytes. This means that the size of the unused space is 21 megabytes. So, which isn't quite the 30 megabytes we need, and therefore we need to delete a file of at least 8 megabytes. The options are we can delete E, we can delete A, we can delete D, or we can delete the whole file system. A and E are too small, so the only thing, and D is large enough. So the idea is you delete the file that is the smallest possible file that will free up the space. So yeah, A and E are too small, so you have to use either D or /, and since D is smaller, you'll use that one. You then have to say what size that file was, and that is your puzzle result, which in my case was 7 megabytes, 421 kilobytes, and 173 bytes. So if I jump over to my Bevy advent calendar, I have it printing out the top directories. Originally I was going to make a full directory tree, but that became a bit too complicated for getting this video done in time. And so it just prints that out, and then in the console it will print out how much free space you have, how much space you need, and then the file name, and then the size of the file you need to delete. Just give it some flavor text. Okay, and then I'll jump over to the code. Oh, wrong file. Over into the code now. So this starts off as normal. Starts off like normal, loading the plugin, setting day 7 for everything, and then we run the read data code. So we get our day's data. We then create ourselves a file system struct, which is down below, which consists of the items and the current path you're pointing to. We then go through each line and we make it peekable. So then while we have lines left, this is so that we can go lines ahead, whereas you can't do that with a for statement. So then we let the words equal the line split by spaces. We get the next word, and we expect there to be at least one word. We then expect the first word to be a $sign. And then based on the word after the $sign, we do either the CD operation, or we peek the next line to see if it starts with a $sign. If it doesn't start with a $sign, we stop doing the loop. But if it starts with a $sign, we split the space and we check if that was a value was dir, meaning it's a directory, in which case we add a directory with the specified name. Otherwise, we pass the size and then add a file with the specified name. This will make a bit more sense when we get to how the file system works. So basically that's our two commands. If we get a nothing or a none, we say that the command needs to be one of those two. We then use file system's item, which is the list of all the items, and we call size. This tells us the total size of the file system. We work out how many small directories there are using the sum of small size, which again we'll get to as a function. Then we say find delete, which will go through, given the specified size, which we worked out earlier, is the difference between our free space and our 30 megabytes. So we pass that in, saying that's the minimum size file we need. It will then go through and find the smallest file that is larger than that value. And then I have a find name just so that I can print the name next to it. And then we spawn in the root directory and all of its entries with the draw fs. I might get around to it before the end of the advent of adding it so that when you select a directory, it will then load that directory's files up so you can actually browse the file system yourself. This just loops through each, spawning in an item with the size and name if it's a file, and a button with the name and dir if it's a directory. The find delete goes through each item. If it's a file, it returns a usize max. If it's a directory, it gets that size, then goes through every entry in that directory, all the sub items, and then works out the minimum of the sub items or 0. And then we say if this sub item is greater than the minimum but not max size, so basically not a null value. I could have, I guess, returned option as the return type, but I figured use size max is perfectly fine. And then if that's true, return the submenu, because it means a file inside it is smaller. And then otherwise return the size if it's greater than the minimum. Otherwise return usize max, which basically just means that it itself is too small, so just make it big. This is about making it fit into the when picking min, we'll always pick a valid file and not an invalid one. And when we iterate through all subfiles, we just recursively call this function. So it descends down to the bottom layer and then works its way back up. Find name does the same thing, but returning the name and just checking to see if the name equals exactly the same thing and recursively traveling down the tree until it finds a file that's exactly the size specified. And it just runs off the assumption that there is only one file with exactly the size. But if there's two, it doesn't really matter which one you delete. So in the file system, there's new, which just creates a new one. So cd will check the input. If it's equal to ... it will pop a value off the current path. If it's equal to /, it will clear the current path. And if it's anything else, it'll add that to the end of the current path. ls is not used because that was for when I was going to make it recursively open files, like so you can click on them. Add file will set the directory to the outermost directory, the / directory, then go through the path trying to find the specified file inside the subdirectory, and if it finds it, it will set that to the current directory, and then otherwise it'll return an error saying it couldn't find the path, or that it is not a path, like not a directory. So if you try to add a file to a file, it won't work. And then finally we open that up and insert the name and file with its specified size. And then add directory is the same thing, but we add a new directory instead of a new file. And then finally we sum small, which runs self items, which is the whole directory .filtered directory with a size of 100,000. And then when we go down to items here, which just is directory and file being a size and a hash map of sub items, size goes through, and if it's a file, returns size. If it's a directory, we'll go through each item in that directory and return its size and then sum them. And then the filter directory takes in a size and returns the number of files, the number of directories that are greater than or equal to that size inside itself. So obviously a file doesn't have any directories inside it, so it returns 0, and then inside a directory, we count the number, we go through each entry and sum the number of directories that meet that criteria, and then we work out its own size and say the sum plus, and then if its size is big enough to count, we add its size, otherwise we add 0, and this just recursively, again, allows for the whole thing to descend, count on its way up, and just bubble the values to the top. Then we just have some file system errors, which is it's not a directory and it's not a file or a directory, like it doesn't exist. And then just a structure, which is about making buttons work in Bevy later. So that's everything you need to solve the puzzle, and it's all printed out. So you'll need sum of small directories as answer to 1, and then delete to free, and that value is the part 2. Okay, and now we will move on to day 8. So the expedition comes across a patch of trees, tall trees, all planted carefully in a grid. The elves explain that this on a previous expedition they planted trees as a reforestation effort. Now they're curious if it would be a good location for a treehouse. First, determine whether there is enough cover here to keep the treehouse hidden. To do this, you'll need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map of the heights of each tree. Your puzzle input. So it gives you a 5x5 grid here. Each tree is represented by a single digit. The value is its height, where 0 is the shortest and 9 is the tallest. The tree is visible if all other trees between it and the edge of the grid are shorter than it. Only consider the trees in the same row or column. That is, only look up, down, left, or right for the given tree. All of the trees around the edge are visible since they are already at the edge and there are no trees to block the view. In the example above, you have the inner 9 trees. It then explains how the visibility works on that, and then it says how many trees. So with the 16 trees visible from the edge and the other 5 trees visible on the interior, there are a total of 21 visible trees in this arrangement. Consider your map. How many visible trees? So I got 1,794. And then Content with the number of trees cover available, the elves just need to know the best spot to build their tree house. They would like to be able to see lots of trees. To measure the view distance from a given tree, look up, down, left, and right from that tree. Stop if you reach the edge or at the first tree that is the same or taller than the tree that you're just considering. If the tree is on the edge, its visibility is always 0. The elves don't care about distant trees taller than those found by the rule above. So basically, the results, the 1,794 trees from the previous question, are the trees you have to consider. Okay, and because it's going to have large eaves that will keep it dry, so they won't be able to see higher than the tree that they're already in. In the example above, consider the middle 5 trees. And so then it just explains again how you would calculate this. And it's saying that the scenic score is found by multiplying together the 4 view distances. So for the there is 4 found. This 5 here has 4 because it's 1, 1, 2, 2, which works out to 4. However, you can do even better because there's another 5 down here that when you look up, you get 2, 2, 1, 2, which comes out to 8. And then it wants you to calculate the tree with the highest value. So I got 199,272. And if we go into my little advent calendar and go to day 8, it takes a little while to calculate because it's of n squared. And then I have a little picture generated that this is the grove of trees. I don't think the whole thing's on the screen because of the fact that it can't quite fit. Otherwise, the trees end up being too small. So I've sort of just maximized the amount of space you can have. And we'll jump into the code. And so this again starts with the basic plugin setup of setting each day to 8. Then we have a resource of trees, which is just a handle to each tree. We then load that from the file of trees and shuffle it using RNG and the seed, like we do with everything else that has loadable assets. We then have a tree, which has an X and Y position and is hashable and partial equaling, so that we can use it in a hash map. We have a way of generating a new tree. We then have a forest, which has a width, a height, and a hash map of trees with their height value. We then have isVisible, which is one of the crucial functions. This goes through and says if any of the values of the tree are equal to 0 or the maximum size, so size -1 or height -1, then it's on the edge and we return false, or I guess true, it is visible. And then we say x, negative x, y, and negative y are all visible, and then go through and see if we can find a tree that is higher than it, and then we set its visibility to false. So this is in the negative x direction, or no, this is in the x direction. So we go from 0 to the tree, and then we go from the tree to the edge of the map, past the other way. So basically from one edge to the tree, from the tree to the other edge, and we skip one just so that the tree doesn't compare to itself and therefore block its own line of view. We then do the same thing for y, like exactly, but obviously swapping out y, and then we just OR the values together, so that if any of the visibility values are true, then the tree is visible. Then there's the scenic function, which is more or less the same, but instead we use a uSize value. We say that the visible from the x is the width minus the tree's x minus 1, which is basically the maximum number of cells the tree can be from the edge. Then we do the same thing with the visible on the xn, which is the trees to the edge. So basically, because the tree, if it's at position, say 3, it must be at least 3 cells from the the 0 edge. And then same for the y. We then go through the same as invisibility, but we enumerate, and we work our way backwards. So we iterate through the same range, but instead we have x equal to tree.x minus x. So instead we start at the tree and then step away. And then once we find x, if we find a tree higher or equal in height, we set that value and then break, which is why we set the values up here to their maximum. So basically, we set them to their maximum, the furthest possible distance the tree could be from any edge. Then we increment away from the tree until we find a taller tree, and we set that as the height if we find one. Otherwise, we leave it at the maximum. We do this for all four directions, up, down, left, and right, and then we multiply the values and return them. We also have an add tree function, which takes in a tree and a height, and then it will set the height and the width of the forest to whichever's larger, the tree's x plus 1 and the forest's width, and the tree's y plus 1 and the forest's height, and then we insert the tree and the height value. Okay, onto the reading data. We get the day's value. We then get ourselves a new forest. We increment through each line as a y value, so each line enumerated, and then we increment through each character, and then so chars enumerated, or indices, and then we forest to add the tree at the x and the y with the char as a u8 minus the offset. This is just a quick way of converting the digits 0 through 9 into the binary values from 0 to 9, because hexadecimal 30 is the offset from 0 in ASCII. So then I print how wide the forest is, just so that I could test things. So the forest is 99 by 99. We then say how many visible, the scenic value, and then also which tree is the most scenic, just again so that I can have a little bit more flavor to it, saying the most scenic tree is the one that's at 3819. So then we spawn our root of our main picture, which with its specifications of being like 85% by 85% with 150 pixels. And then for each tree, we specify, for each tree and height, we iterate through all the trees in the forest. We then filter those tree values by if the forest is visible, and then we spawn in a sprite for the tree, and we calculate its scenic value. And then if the scenic value is better than the current scenic value, we set the new scenic value, and we set this tree as the scenic tree, and we increment the number of visible trees by 1. We then print out how many visible trees there are and which is the most scenic tree. So as you can see in the thing, in the console output, this is answer to 1, and this is the answer to question 2. I hope you've enjoyed this video, and like, comment, subscribe, and I'll see you in the next one.